The most common form of signal processing is Fourier analysis. In Fourier analysis, we take the set of complex exponentials as our basis functions. To justify this, we need to prove exponentials 1 are orthogonal to one another, and 2 span the set of all possible functions. First, let's prove they're orthogonal. To do this, we'll just plug in two different complex exponentials into our test for orthogonality and see if it is equal to 0. Let g of x equal e to the j mx and f of x equal e to the j nx, so that the integral from -infinity to infinity of g star x f of x dx is equal to the integral from -infinity to infinity of e to the minus j mx e to the j nx dx. Use the rules of exponentials to combine the terms. Next, we'll use the fact that complex exponentials are periodic. Because they're periodic, we only need to show that the inner product is 0 over 1 period. A period is one cycle of the unit circle, which occurs every time the exponent reaches some integer times 2 pi. So to solve for the period, we set the exponent to 2 pi and solve for x. We then change our limits of integration to just one period of the complex exponential. We use our results concerning antiderivatives of an exponential, and we evaluate the antiderivative from 0 to 2 pi over n minus m, invoking the fundamental theorem of calculus. After a few steps to simplify the right-hand side of the equation, we can show that the integral of the complex exponential over one period is equal to 0. Therefore, the inner product of e to the j mx and e to the j nx is 0 for all m not equal to n. We've proven that the set of complex exponentials are orthogonal to one another. Here we argue that the set of basis functions e to the j omega x can be combined linearly to span all functions. A rigorous proof would require considerably more linear algebra than we're covering, so I'm just going to explain why it makes sense to me. Any function can be represented as an ordered set of points. We're going to argue in the continuous case. The argument in the discrete case follows, but requires a deeper consideration of the cyclic nature of complex exponentials, which we haven't developed yet. Saying a function is a series of points is the same as saying a function is a series of delta functions. So if you believe that any function can be represented as a series of delta functions, all we need to do is show that the delta function can be represented by a complex exponential in a unique one-to-one relationship. Let's set up what we know and don't know in system form. Our input is the general form of a scaled and shifted delta function. It goes into a box and out comes a complex exponential of the form a times e to the j tau omega. The question now becomes, what set of operations can we do to a delta function that will output a unique complex exponential? The answer is known as the continuous time Fourier transform. We'll introduce it more formally later. Let's put our input into the box and simplify. The trick is to recognize that the only time the argument of the integral is not equal to 0 is when the argument of the delta function is 0, which is when t equals tau. Therefore, we can ignore all other t except when t equals tau. So just plug tau in for our instances of t. But that means we no longer have a variable with respect to integration, and we can drop the integral. We are left with the output, which is a times e to the negative j omega tau. We can see that the a and the tau are both preserved in the output, so the output must be unique to the input. To summarize the steps of the argument, any signal can be considered as a series of delta functions. All delta functions have a one-to-one relationship with a complex exponential through the continuous time Fourier transform. Therefore, any signal can be represented uniquely as a series of complex exponentials. What we are doing is changing our viewpoint of the signal. We are looking at signals in terms of complex exponentials instead of in terms of a series of points. We are just translating an idea from one language to another. We have spent the last few minutes verifying that this is a good way to interpret signals because complex exponentials are orthogonal to one another and span the function space, meaning, respectively, that complex exponentials are efficient and logical and can accurately describe all functions through linear combinations.